Imagine standing on the edge of an ancient African forest about 6 million years ago. The trees are thinning. The fruit, sweet, abundant, easy, is becoming harder to find. The climate is changing, slowly but relentlessly, and somewhere in that uncertain borderland between forest and open grassland, something remarkable is happening. One creature is beginning to stand up. That creature is us. Or rather, it's the ancestor that would eventually become us. And the story of how we got from there to here, from knuckle-walking ape to the species that built cities, composed symphonies, and landed on the moon, is one of the most extraordinary stories ever told. It's the story of the human body. Let's begin. Here's a question that sounds simple, but has puzzled scientists for generations. Why did we start walking upright? We share over 98% of our genetic code with chimpanzees. A chimp is fast, agile, immensely strong, an expert climber. By comparison, early humans were slower, weaker, and frankly terrible at climbing. So what was the evolutionary payoff? Why trade all that primate power for two awkward legs? The answer, it turns out, has less to do with brains or tools, and everything to do with dinner. Between 10 and 5 million years ago, Africa was cooling. Rainforests were shrinking. The lush, fruit-filled canopies that ape ancestors depended on were giving way to drier woodlands and open savannas. Ripe fruit became scarce, and the ancestors who could stand upright, who could reach higher, walk farther, and use their hands to dig up underground tubers and roots, had a critical survival advantage. Studies show that chimpanzees expend roughly 4 times more energy walking a given distance than humans do. Their bent-kneed, swaying gait is extraordinarily costly. Early hominins who walked more upright, even slightly, could travel farther on the same calories. In a world where food was dispersing across vast landscapes, that efficiency wasn't just convenient. It was the difference between life and death. The oldest evidence of upright walking comes from creatures like Ardipithecus, Ardi, a small ancient hominin whose partial skeleton was recovered from Ethiopia and dates back 4.4 million years. Ardi was fascinating precisely because she was a hybrid. Her pelvis showed the hip structure needed for upright walking, but her feet still had a grasping big toe for climbing trees. She wasn't fully committed to either world, a cautious evolutionary experiment tiptoeing between two lifestyles. Bipedalism came with real costs. Pregnant females faced new challenges. A shifted center of gravity, back pain, instability. Early hominins lost speed and climbing agility. Standing on 2 legs makes you conspicuously vulnerable on an open savanna. And yet, the benefits won out. For millions of years, these upright walkers thrived and diversified. The dinner problem. Around 4 million years ago, a group called the Australopiths emerged across Africa, and they were remarkable creatures. Think of them as a bold evolutionary experiment. Ape-like in brain size and face, but committed bipeds who walked the open woodlands with surprising efficiency. Lucy, the famous Australopithecus afarensis fossil, is among the most celebrated of these beings. She stood about 1 meter tall, walked on 2 legs, and had a brain roughly the size of a large orange. She was not human, but she was heading in our direction. What drove the Australopiths was the food problem. Africa was drying further, and the preferred menu of ripe tropical fruit was becoming increasingly unreliable. So these early ancestors did something ingenious. They got flexible. They began digging. Underground storage organs, tubers, bulbs, corms, rich in starch, available year-round, requiring effort to extract but worth the investment. Their bodies reflect this dietary shift in striking detail. Australopith cheek teeth were enormous, up to twice the size of a chimpanzee's, with enamel 3 times as thick. Some robust species, like Australopithecus boisei, earned the nickname Nutcracker Man for their massive grinding molars. Their cheekbones flared wide to anchor powerful jaw muscles. Their faces, in some species, looked almost armored, built to process the toughest, most fibrous foods the savanna could offer. And yet they were still partly tree creatures. Short legs, long curving fingers, powerful forearms. The Australopiths walked the ground but slept in the trees, foraged below but retreated above when predators prowled. They were bridge creatures, caught between 2 worlds, perfectly suited to neither, and yet surviving brilliantly in the space between. The rise of the hunters. About 2.5 million years ago, something shifted dramatically. The Ice Age arrived, not in one catastrophic moment, but as a long, slow escalation of climate instability. Forests retreated further, grasslands expanded, and the Australopith strategy of eating tough plants began hitting its limits. Enter the genus Homo. Homo habilis, handyman, showed the first tentative steps toward what we'd recognize as humanity, a slightly larger brain, hands capable of shaping stone tools. Then, around 1.9 million years ago, Homo erectus strode onto the scene, and everything changed. Longer legs, shorter arms, a modern striding gait. The first hominin to look, in body at least, recognizably like us. And critically, Homo erectus was eating meat. Stone tools dating back 2.6 million years bear the evidence. Cut marks on animal bones, marrow extracted from cracked femurs. Meat was a revelation. Dense in calories, rich in protein and fat, it provided nutrients that no amount of tuber digging could match. Hunting and scavenging opened an entirely new energetic frontier. But meat came with challenges. You can't outrun a wildebeest in a sprint, so early hunters developed something far more powerful than speed: endurance. Homo erectus was built to run. Not fast, but forever. Sweat glands proliferated, body hair thinned to allow evaporative cooling. The Achilles tendon grew long and springy, storing and releasing energy with each stride. The big gluteal muscles, what we know as the buttocks, enlarged dramatically to stabilize the torso during running. Even the inner ear changed, growing larger canals to keep the head steady while the body pounded across open ground. The strategy was called persistence hunting. Chase prey in the heat of the day, over miles and miles, until the animal, unable to sweat like a human, overheats and collapses. It sounds almost too simple, but it worked for hundreds of thousands of years. And with meat came something else: cooperation. Sharing food, division of labor, males hunting, females gathering, grandmothers providing food supplements to grandchildren, enabling mothers to wean infants earlier and bear more children. The social bonds of early Homo were tightening. Community was becoming survival. How to shack the brain problem. Now here's where the story gets truly extraordinary. Large brains are expensive. The human brain is only about 2% of our body weight, but it consumes 20 to 25% of our resting energy. That's an extraordinary metabolic cost. To support that brain, humans evolved to store fat, far more than any other primate. Human infants are born pudgy, with 15% body fat. Those fat reserves exist to fuel the enormous energy demands of a growing brain. And brains do grow, slowly, beautifully, over many years. A human newborn's brain quadruples in size over the first 6 or 7 years of life. Childhood, in evolutionary terms, is a luxury, an extended developmental window that no other primate enjoys in quite the same way, precisely because the brain needs time to wire itself for the complex social and ecological world it must navigate. By the time Neanderthals and early modern humans emerge, roughly 200,000 years ago, brain volumes had nearly doubled from Homo erectus levels. These were large-brained, fire-using, spear-hunting beings of considerable intelligence. Neanderthals buried their dead. They crafted complex stone tools. They were not primitive brutes. They were sophisticated people adapted to Ice Age Europe's brutal conditions, with stocky bodies built to conserve heat and massive noses to warm frigid air. And yet, they vanished. What made us different? Around 50,000 years ago, something ignited in our ancestors that changed everything. Cave paintings bloomed in southern France and Spain. Bone needles appeared, enabling sewn clothing. Fishing hooks, lamps, musical instruments, long-distance trade networks. Symbolic art, abstract thinking, cultural explosion. Modern humans weren't just physically slightly different from Neanderthals. They had rewired the way culture worked. The temporal and parietal lobes of our brains were subtly larger, supporting richer language, better memory integration, more sophisticated theory of mind, the ability to model what other people are thinking, to cooperate on a scale no other species could match. And unlike biological evolution, which moves at the glacial pace of generations, cultural evolution moves at the speed of an idea. A better spear tip, shared across a group, becomes universal within a generation. A new hunting strategy spreads faster than any gene ever could. By 15,000 years ago, Homo sapiens had colonized every continent except Antarctica. Neanderthals, Denisovans, the tiny hobbits of Flores Island, all gone. one human lineage remained, us. Standing upright to reach fruit in a thinning forest, grinding tubers with enormous teeth, running prey to exhaustion across the savanna, growing enormous, expensive, beautiful brains, telling stories around a fire. Every chapter of our biology is a chapter of this story, a story not of triumph exactly, but of relentless, contingent, improbable adaptation. We are not the strongest animal, we are not the fastest, we are not even the largest brained in absolute terms, but we are the most culturally inventive creature that has ever lived on this planet. And that capacity to learn, to share, to imagine, and to cooperate is what made us unmistakably human. So that's where we came from. 6 million years of stumbling, adapting, and surviving. From a knuckle-walking ape on the edge of a thinning forest, to a species with the cognitive power to paint cave walls, sew clothing, navigate oceans, and reimagine the world entirely. By 15,000 years ago, Homo sapiens had done something no other animal had ever done, colonized virtually every environment on Earth, from Arctic tundra to equatorial jungle, using not claws or speed or brute strength, but culture. It is, by any measure, a breathtaking achievement. But here's the thing about being the most culturally inventive species that has ever lived. The inventions don't stop. And not every invention is good for us. Because the same cultural engine that took us from stone tools to cave paintings to long-distance trade networks kept right on accelerating. Through the invention of agriculture 12,000 years ago, through the Industrial Revolution 2 centuries ago, and into the hyper-processed, screen-saturated, chair-bound world most of us inhabit today. And our bodies, those ancient, exquisitely adapted bodies we've just spent an episode exploring, have not kept up. They couldn't. Evolution moves in geological time. Culture moves at the speed of an idea. And the gap between the two is now so large that it's generating something scientists call evolutionary mismatch. A growing collision between the biology we inherited from millions of years on the African savanna and the environments we've built in the last few thousand years. That collision has a body count. In part 2, we follow the story forward into the fields of the first farmers, the factories of the first industrialists, and the doctors' offices where the consequences of both revolutions are still being tallied. We'll meet a concept called disevolution, the troubling loop by which modern culture treats the symptoms of its own diseases without ever fixing the cause. It's a harder story than part 1, but it's a necessary one, because understanding how we broke the body is the first step toward figuring out how to protect it.